Hello, my name is Arya Gupta, and I'm presenting the paper Lattice Linearity of Multiplication and Modulo. In this presentation, we'll discuss synchronization. Specifically, we'll discuss eliminating synchronization, some ways how to do that, and what the theory behind those ways looks like. So we'll start with a brief discussion on the structure of a multiprocessor system. There are several nodes, and every node contains guards and corresponding actions. And the structure of a guarded action looks like this. G implies A sub C, where G is the guard. G is a Boolean expression over variables of multiple processes, and A sub C is the action, and it is executed by some process I if I evaluates the corresponding guard to be true. And A sub C makes changes to the values of the variables of node I. There is an underlying assumption in most distributed system algorithms and parallel processing algorithms that G is evaluated in the current state. What it means is that the values of variables of the nodes on which G is evaluated are assumed to be the latest value, to be the fresh values. To ensure that this assumption is enforced, is deployed, we need synchronization. Synchronization is needed to ensure that the data is read in a consistent fashion. So moving ahead with our discussion on asynchrony, what do we want to do? We want to design the guards in such a way that they enable the nodes to take actions such that a value once discarded, that is discarded forever. In this figure, we present a system of several nodes, and let's look at the behavior of node 2. Node 2 transitions from local state 1 to 2 to 3 and so on. So let's look at one of the transitions, transition from 3 to 4. These nodes, how they are able to discard some local state and move ahead is as follows, is that the predicates can determine that a particular local state is not good for any global state, and only then they make a move. So when 3 moves to 4, when node 2 moves from 3 to 4, then it only moves when it decides that 3 is not a good state for any optimal global state. So if in case it moves, it decides that state 4 is also not good, then it does not have to move back to state 3, 2, or 1, because it already decided that states 1, 2, and 3 are bad states for all optimal global states. So it only has to move from 4 to 5. Now here we see that so if the predicate can determine that a local state is not viable for any optimal global state, then we can allow the nodes to run in asynchrony. Now here we see that the local states of the nodes, they are forming a total order. And as a result, the global states form a lattice. The node that is in a bad state is called an impedanceable node. The word impedanceable is a conjunction of two English words, impediment and indispensable. And we call this node impedanceable because it is an impediment to progress if it does not execute, and it is indispensable to execute for progress. Let's look at an example problem, the minimal dominating set problem. And we have an input, a graph G. A node I is called dominated when it is in the dominating set, or if one of its neighbors is in the dominating set, and we want to make the whole graph dominated, meaning we want to dominate all the nodes, but minimally. We are going to consider this for this graph. It's a graph of two nodes connected to each other by an edge. And let's assume that node 1 executes this algorithm. When node 1 sees that both the nodes are out, then node 1 turns itself into the dominating set. And if node 1 sees that both the nodes are in, then it turns itself out of the dominating set. This action makes both the nodes dominated, and the second action makes the dominating set minimal. And a similar algorithm can be implemented for node 2. Now, let's see the behavior of this algorithm when it is implemented without interleaving executions and without locks. So let's look at state 4. Both the nodes are out. Now, if one reads the state of node 2, then it will see that both the nodes are out and it will decide to move in. And in case if 2 sees reads the state of node 1, again it will see that both the nodes are out, and 2 will also decide to move in. So state 4 will transition to state 3. In state 3, both the nodes are in, and if in case they read the states of each other at the same time again, then both these nodes will move out and state 3 will transition to state 4. And this can continue forever. We see that state 4 is infeasible, state 3 is feasible but not optimal, and states 1 and 2 are optimal. So if only one node is allowed to execute at a time step, then we can guarantee convergence. But if both the nodes are allowed to execute simultaneously, then the global state may never converge. Moving ahead with our discussion on asynchrony, Garg in 2020 introduced lattice linear problems. And the example problem that we are going to discuss is the stable marriage problem. In stable marriage problem, there are men and there are women. Men propose to women and women accept or reject that proposal. Men have preference lists and women rank men. So in this example, we have 3 men and 3 women. All the men start with their first choice. So the initial global state is 1, 1, 1. So A is proposing to Z, J is proposing to Z, and T is proposing to K. Now we see that A and J have a conflict because they are proposing to the same woman. But let's see what Z has to say about it. Z prefers A more than J. So J is impedanceable. J has to move to the next choice. So J moves from 1, local state 1, to local state 2. Now J is proposing to K, A is proposing to Z, and T is proposing to K. Now there is a conflict between J and T, but let's see what K has to say about it. K prefers J more than T. And so now T has to move to the next choice. So T moves from local state 1 to 2. And now the system is in the global state 1, 2, 2. So finally A is proposing to Z, J is proposing to K, and T is proposing to M. Now there is no conflict. 1 to 2 is an optimal state and we have reached it. Here we see 3 properties. The first property is all the nodes, the local state that they visit, those local states are forming a total order because the men are only moving from 1 to 2 to 3 and there is no point coming back. The second property that we see is that the system has to initialize in the state 1, 1, 1. If we initialize in some other state, then we might not be able to reach the optimal state. The third property that we see here is that if we look at any suboptimal global state, we will be able to point out the impedanceable nodes. And this third property is what makes this problem a lattice linear problem. In this paper, we consider the following questions. What other problems can be solved under lattice linearity? Are there problems that allow self-stabilization? So the first problem that we are going to discuss is Karatsuba's multiplication algorithm. We want to multiply two numbers n and m, and we are going to look at them as bit strings as well as numbers. And we're going to assume that those bit strings are of equal length. Karatsuba divided n to two substrings a and b, and m is divided to c and d. And a and b, c and d are of approximately equal sizes. And the multiplication of n and m looks like this: a times c times z square. This is the first term. The second term is b times c plus a times d, and multiplication of this with z. And the third term is b times d. Z is some power of 2. So we can consider this multiplication as a left shift operation. And so finally we are left with four multiplications. However, this middle multiplication here, it can be evaluated using the other multiplications that we have performed like this: a plus b times c plus d minus a times c minus b times d. So we have reduced from 4 multiplications to 3 multiplications. How we parallelize this? The computing nodes induce a trinary tree among themselves. The base case is that root will read the value of n and m, and the 3 multiplications are thrown to 3 different children nodes. And this method was proposed by Cesari and Meader. Here we see an example. Node I contains the value of m and n, and node I pastes the values of respective a and c, b and d, a plus b, c and d. I'm sorry, a plus b and c plus c, d to these 3 nodes as m and n. And here we see that m and n, all these 3 nodes, these variables, these 6 variables can be initialized arbitrarily. And if they do not tally with the initial m and n of node I, then we have that node I is impedanceable, and it rewrites those values if that happens. So this was how the values m and n moved down in the tree. Now we'll see how answer moves up. So the children node evaluate the multiplication that they were supposed to do, and node I uses those answer values and computes the final answer using addition and subtraction. Here we can allow the answer variable of node I to be initialized arbitrarily, and if this variable, the value stored here, does not tally with the values of the children, the answer variables of the children, then it will be corrected using the guards. So if that happens, if there is a mismatch, then node I again is impedanceable. So this was algorithm for multiplication using Karatsuba's method. Now parallelized modulo, we are going to look at modulo. We want to compute n mod m, and n is divided into 2 substrings a and b, which are of approximately equal length. and we can evaluate n mod m using this expression, a times 2 to the power size of b plus b under mod m. So a binary tree in this case is induced among the processing nodes. In the base case, the leaves of this tree read the substring of n contiguously, and they read substrings of size half the size of m and store that as answer. Otherwise, a node I reads A as the answer of the left child and B as the answer of the right child, and it computes the answer using the same expression. Here is an example. This is an example. This is the root node for the evaluation of 11011 mod 11. So node 1 is the root node, and node 1 uses the answer values of node 2 and node 3 to evaluate the final answer. We have power here to help with that computation. For this level, for node 2 and node 3, the power is 100. And it means that both the children of node 3 and both the children of node 2, the answer values are of 2 digits, but under mod 11. Similarly, for node 1, the power is 1 followed by 4 zeros. And it means that the value of the answer variable of node 2 and node 3 are of 4 digits, but under mod 11. And these power variables are also kept under mod 11. So what happens here is the answer from node 2 from the left child is multiplied with the power, and then it is added to the answer from the right child. And that's how we get the final answer. So we see that the sizes of both A and B are upper bounded by the size of M. And similarly, the power is also upper bounded by the size of M. So here we can allow the answer value of node 1 to be initialized arbitrarily. And if it does not tally with the answer values of node 2 and node 3 in this example, then we have that node 1 is impedanceable. So if the answer of parent does not match with the children, then the parent node I is impedanceable. So this was the working of parallelized modulo operation. There has been more work in the area of lattice linearity. We have looked at problems that are not lattice linear, for example, minimal dominating set. So we look at this example again of 2 nodes connected to each other by an edge. Both the nodes are out. One can move in which case system moves to an optimal state. 2 also could move in, and the system would move into an optimal state. If 2 moves in, then 2 is impedanceable. If 1 moves in, then 1 is impedanceable. So in fact, we can see that it cannot be determined which node is impedanceable. To address this, we introduced eventually lattice linear algorithms in SSS 21. These algorithms are able to induce lattices in a subset of the state space, and that's why we have the name eventually lattice linear. And we introduced fully lattice linear algorithms in SSS 22 and SRDS 23. SSS 22 was a brief announcement, and the full conference paper was accepted in SRDS 23. What these algorithms do is they impose lattices among the global states. And fully lattice linear algorithms are able to impose lattices in the entire state space, as opposed to eventually lattice linear algorithms. In conclusion, we have that lattice linearity implies that said algorithm can be run without synchronization among the nodes. Modulo and multiplication are among the fundamental mathematical operations, and we showed that these problems are lattice linear, and the algorithms we showed can be run in asynchrony because they exploit that lattice linearity. Lattice linearity in their parallelized versions can be extremely useful in computational applications. This is because we remove the requirement of synchronization among the nodes for these algorithms. We have some open questions. What other problems can we apply lattice linearity in? And what existing algorithms exhibit lattice linearity? And we are actively working in this area. Thank you.